Hello, my name is David Patterson. I'm a retired research scientist. I have a degree in applied mathematics, engineering, and I have a PhD. What I'm going to talk about now is the summary of the results from 2 years of research into the topic of infinity. I'm going to keep it very simple, so don't worry about difficulty of understanding it. Infinity is a huge topic, not because infinity itself is huge, but because there are so many different systems of infinite numbers. There are at least 12 different systems of infinite numbers, and often these agree with one another and often they don't agree with one another. Some systems of infinite numbers have infinitesimals, and some systems of infinite numbers don't have infinitesimals. Some systems of infinite numbers have infinity is equal to infinity plus 1, and some systems of infinite numbers have infinity is not equal to infinity plus 1. The infinity that you taught in school is not particularly intuitive and not particularly useful in applied mathematics. So what I'm going to do is introduce you to a system of numbers that is useful and can be and has been used in applied mathematics. This type of infinity is called ordinal infinity. There are other names, but ordinal infinity is simple enough. Now this has been around for a lot longer than the infinity you taught in school, perhaps 200 years longer. But back then it wasn't called ordinal infinity, it was just called infinity. Now there's a good chance that you've already encountered a type of ordinal infinity, but you don't know that you know about it because it wasn't taught as ordinal infinity and it wasn't even taught as infinity. It's the order of magnitude, big O notation, order of magnitude symbol. If you find anything in the talk that you don't understand, just skip it and the rest of the talk will make perfectly good sense. And if you already know what an ordered field is, then you're already 99% of the way to knowing what ordinal infinity is. If you don't, then don't worry, I'll explain it. If you don't know what a complex number is, that's okay. You don't need to know that. But it would help if you know the difference between a natural number and a real number. So if you don't know that, I suggest going and looking it up. But most people will know that. Now I'm going to start off with the difference between cardinal and ordinal. A cardinal number is a number like 1, 2, 3, 4, 5, etc. An ordinal number is a number like 1st, 2nd, 3rd, 4th, 5th. The cardinal numbers can be rearranged in any order, like 3, 14, 15, 9, 2, etc. But ordinal numbers can't be rearranged, they're always in order. So 1st, 2nd, 3rd, 4th, 5th. Now if you think of the axis of a graph, for instance, the numbers on the axis of a graph are always in the same order, always in order. And that means that the axis of a graph is showing ordinal numbers. The difference between cardinal and ordinal affects infinity because, well, how do you rearrange infinity? And there are quite a few different ways that have been invented, but it's actually easier if you don't bother to rearrange infinity in the first place. "99.9% of the times you encounter infinity, it will be written using the lemniscate symbol." The infinity symbol, or the lemniscate symbol, was originally chosen because infinity folds back on itself in terms of naive infinity. Once you get to the end, 1 over 0, you start at the other end, minus 1 over 0, minus infinity. So if you're using naive infinity, then you have to have a minus infinity, which is the same as infinity. As you get further in school, you'll encounter what is called cardinal infinity, invented by Cantor, of which the simplest cardinal infinity is aleph null, which is written using the first Hebrew symbol aleph and subscript 0. You will never encounter ordinal infinity. But ordinal infinity is written using the last Greek letter omega. And this was chosen not just because it's the last Greek letter, but because it's the bottom half of the infinity symbol. Ordinal infinity is the most useful of all. Now let's talk about the infinity that you were taught in school, which I've here called naive infinity. In early school, we are taught that infinity equals infinity plus 1, to infinity and beyond. That infinity is 1 divided by 0, and that minus infinity is different from infinity. The statement infinity equals infinity plus 1 is known as shift invariance. Any number which is the same as that number plus 1 is called shift invariant. I'm going to show later that there are some types of infinity that are shift invariant and other types of infinity that are not shift invariant. Naive infinity is self-contradictory because minus infinity equals infinity, but we're also taught that minus infinity is not equal to infinity. Minus infinity is used in cases such as the following. Well, the total probability is 1. That is, the integral of probability over all the possibilities sums to 1. In order to maintain minus infinity is not equal to infinity, it becomes necessary to discard naive infinity and replace infinity equals 1 over 0 with 0 equals infinity times 0 equals 0 times infinity. So 0 times infinity is not undefined when you have an minus infinity which is not the same as infinity. But that's discarding naive infinity. In later school, we learn about Cantor cardinal infinity, of which the simplest is called aleph null. This type of infinity has the following properties. 1 plus aleph null equals aleph null equals aleph null plus 1. As with naive infinity, aleph null is shift invariant. 2 to the power aleph null is not equal to aleph null. The second statement that 2 to the power aleph null is not equal to aleph null is used to prove that there are more real numbers than natural numbers. And you may have encountered the proof because there are a lot of discussions that say that. Many mathematicians have built on Cantor's cardinal infinity to find more cardinal infinities. Often these have been given funny names, including lambda shrewd, shrewd infinity, ethereal infinity, subtle infinity, almost ineffable infinity, ineffable, ineffable, totally ineffable, remarkable, strong and tall cardinals. I keep imagining going up to a cardinal of the Catholic Church and asking, "Are you an almost ineffable cardinal?" In the very same paper that the mathematician first published his cardinal infinity, he also presented his ordinal infinity. Now, Cantor ordinal infinity, as I'm looking here, has a bit of a difference to the ordinal infinity I'm going to use for the rest of the paper. Ordinal infinity is written using this small Greek letter omega. Cantor's ordinal infinity has the following property: 1 plus omega equals omega. But omega is not equal to omega plus 1. So 1 plus omega is not equal to omega plus 1. And the fact that two numbers aren't the same around an addition sign when they're swapped in order is called being non-commutative. In normal mathematics, 1 plus a number equals that number plus 1. You may or may not be familiar with Hilbert's Hotel. Hilbert's Hotel is a hotel with an infinite number of rooms. In order to accommodate a new guest into a hotel already full, he asks the guest in room 1 to move to room 2, room 2 to room 3, room 3 to room 4, etc. The new guest moves into room 1. So, an infinite hotel, one new guest can still fit in that infinite hotel. Now, but to do that, this requires an infinite number of room shifts, which is a problem. It is exactly this thinking that led Cantor to come up with his ordinal infinity. In fact, Hilbert's Hotel can be thought of as an illustration of Cantor's ordinal infinity. Hilbert's Hotel can accommodate a new guest in room 1, so 1 on the left plus omega equals omega. But the new guest cannot move directly into room infinity plus 1. So you cannot put a new guest into the high-end room of Hilbert's Hotel because there is no highest room. So omega is not equal to omega plus 1. Now there are several different alternative interpretations of Hilbert's Hotel. One interpretation is that Hilbert can't move put guest 1 into room 2, because then that would be saying that 1 equals 2, which obviously is wrong. Another way of looking at Hilbert's Hotel is that you count the number of rooms rather than the number of guests. Hilbert doesn't move the rooms around, keeps all the rooms in the same place. So the number of rooms is always going to be the same. So if you add 1 to the number of rooms, it's not the same as the number of rooms originally. Third take on Hilbert's Hotel is that the speed of light is finite. so Hilbert can only tell a finite number of guests in his hotel to shift rooms. In this case, not even a single new guest can be accommodated in an infinite hotel already full. And in that case, infinity is not equal to 1 plus infinity. And 1 plus infinity is equal to infinity plus 1. From now on, what I call ordinal infinity, is going to have infinity is not equal to 1 plus infinity, and 1 plus infinity equals infinity plus 1. This turns out to be much more use than having 1 plus infinity is not equal to infinity plus 1. Now, an ordered field is a very, very common entity in pure mathematics. You can find it in any pure mathematics course. Start first with a set. A set is any collection of entities. So in early school you might say that a set is an apple, an orange, a banana. But you can't say that an apple is less than an orange, or an apple is more than an orange, or an apple equals an orange. So you don't have an order in a set like that. However, if the set contains numbers, then you can have them. 1 is less than 2, 2 is greater than 1, 3 is equal to 3. What mathematicians call a field is a collection of numbers that behave nicely. Numbers that satisfy the usual rules of addition, subtraction, multiplication, and division. An ordered field is a field that is also an ordered set. So the usual rules of addition include commutative addition. Usual rules of addition include infinity plus 1 equals 1 plus infinity. So Cantor's ordinal infinity is not a field, but what I'm here calling ordinal infinity is a field. And we can generate this field by just applying the operations of addition, subtraction, multiplication, and division to the real numbers plus a selection of infinite numbers. Now, there's a good chance that sometime in your life you've already come across the order of magnitude symbol. You may have even used it. In school you learnt that the function x squared increases towards infinity faster than x. And later you learned that the function 2 to the power x increases towards infinity faster than x to the power n for all values of the natural number n. So we write this as order of x squared is greater than order of x, and order of 2 to the power x is greater than order of x to the power n. This is a statement using ordinal infinity. You can see that it's not true for naive infinity, because in naive infinity you don't have infinity squared is greater than infinity. And you can also see that it's not a function of cardinal infinity, because Aleph null squared is the same as Aleph null. Aleph null squared is not greater than Aleph null. Big O notation for order of magnitude is heavily used in computer science and is also used in many other places, such as physics. This is a bit of a complicated slide, but let's see how we go. When I say for sufficiently large x, that's actually a short way of saying that there exists an n such that for all x greater than that natural number n. And one way to define ordinal infinity and ordinal infinite numbers is to say that if something is true for sufficiently large x, then it is also true for infinity. So, for sufficiently large x, infinity is less than infinity plus 1 because x is less than x plus 1. The infinitesimal 1 on infinity is greater than 0 because 1 on x is greater than 0 for all large x. Infinity divided by infinity equals 1 because for all large x, x divided by x equals 1. 0 times infinity equals 0. And we also say that there exist such numbers as the square root of infinity, the logarithm of infinity, and e to the power infinity. All right, a little history. The practical use of infinitesimals dates back to the time of Newton, 1666. Now, infinitesimals do exist in the field of ordinal infinite numbers, but they don't exist in naive infinity, and they don't exist in cardinal infinity. So what Newton was talking about back in 1666 was in fact the use of ordinal infinite numbers as applied through infinitesimals. The mathematics behind ordinal infinity dates back to 1870, or rather, I should say, specifically the use of orders of infinity, that is, x is less than x squared, dates back to a chap called de Bois-Reymond in 1870. The symbol omega started being used for ordinal infinity back in roughly the year 1873. So none of this is particularly new. I'm not inventing a new mathematics here or anything. I'm just bringing up to date what has been done a long time ago. The mathematically most advanced system of ordinal infinite numbers comes from Abraham Robinson and was written about in the 1970s. And these are known as hyperreal numbers. So if you hear the term hyperreal numbers, think ordinal infinite numbers. I'm going to discuss the hyperreal numbers briefly in part 2 talk. Why are we not taught about this? Well, largely because Cantor published faulty proofs that were later demolished, claiming that his ordinal infinity is the only ordinal infinity. And because Cantor's ordinal infinity is essentially useless from an applied maths point of view, the whole topic of ordinal infinity was dropped from the maths curriculum. But it still survives through the order of magnitude symbol and elsewhere, from the ends of the real number line. Some take-home messages from this part 1 talk are: every time you use minus infinity, or if you use the ends of the real number line, for example, as the axis of a graph or as the end of an integral, or you use the order of magnitude symbol, big O, then you're using ordinal infinity. So it's not something totally out of the ordinary. This is something that is really quite ordinary. Ordinal numbers are literally numbers placed in size order. Ordinal infinity is written omega, little omega. Infinitesimals exist and make calculus easier to understand. Infinity is not equal to infinity plus 1, and infinity times 0 equals 0. Infinity can be manipulated mathematically, and the square root of infinity and log infinity exist as separate infinite numbers. If you can remember that, then that's great. This is the end of the part 1 talk.